Okay. Hello, everyone. I'm Marios Kiatos. I'm the co-founder of Progressive Robotics. It's a pleasure to be here today. I'd really like to specially thank Professor Tefas for the invitation. So in this presentation, I will share the story of progressive robotics from our beginnings at the university and to how we are evolving and scaling as we move forward. So our journey began right here at the Robotics and Automation Lab in the Department of Electrical and Computer Engineering. For us, everything started in 2020. We were a small team of PhDs and postdocs doing our research. In parallel with our research, we ran a project called ProgHRC, which focused on human-robot collaboration. So our goal was to understand how robots could operate safely and intelligently alongside people. So to test our ideas, we brought our early systems to local exhibitions, observing how people interacted with our technology. By 2021, we had our first real prototype. As you can see here, we used a collaborative robot to handle boxes. So we implemented a teaching by demonstration approach. A human operator would physically guide the robot arm through a trajectory, and the robot learned instantly how to execute the path and generalize it. So we also integrated the computer vision by placing a camera above the conveyor to detect and estimate the 6D pose of the box. So and the system would detect the boxes. The robot would grasp the first box on the conveyor and then place it into the carton, doing fully autonomously. So it keeps continuous until the carton is fully is full. So following in those footsteps, progressive robotics was born in 2023 when Fotis and I decided to take that step. We formed a core team of 6 people and made a deliberate shift from pure research to engaging with real customers and real world problems. So we visited a lot of factories in Greece, telling them we have a solution for your packaging lines. The feedback was eye-opening. While they recognized the innovation that we have done, they told us that the speed for packaging was too high for the robotic arms. So we hit a wall because the physics of the manipulators couldn't match the throughput their operations demanded. And then we made a pivot. The market gave us a clear challenge. Can you do palletizing? Of course, we can. We said we can do it because palletizing is like packaging on a larger scale. So the math, the kinematics, and the logic were transferable from our previous work. However, as you know, hardware is hard. So deploying in a live industrial environment taught us lessons you can't learn in a lab and shaped the way we approach solutions today. The first deployment had a lot of bugs. So we iterated, we fixed the bugs, and we refined the code. In 2024, our first deployment went fully live. The validation, the same customer that at first was skeptical ordered a second system. This was our first major win and a clear signal that we were on the right track. So some things about our single case palletizing software. What made our solution stand out from established competitors back then? So we had an advanced path planning, which ensures that the trajectories that we generate are collision-free. And also, we had the feature for multi-pick, which allows robots to pick and place multiple items at once, which maximize throughput. So these features translate directly into optimized cycle times. The result is an intuitive, user-friendly software which allows a new palletizing recipe to be created in just 60 seconds. And this is a walkthrough in the single case palletizing software. So at step one, the operator creates a new box type and defines the batch size. The batch size is the multi-pick feature that I described earlier. At step two, the operator selects the pallet type and sets the number of maximum layers. At step three, our software calculates all valid patterns instantly, and the operator chooses one. And finally, before the robot moves, we run a simulation where the full pick and place trajectory is calculated for every box on the pallet. This verifies reachability and cycle time and allows the operator to exactly see how the robot will move before deployment. And then we hit deploy and the robot starts palletizing. So in essence, what we have done is that we built an abstraction layer hiding complex kinematics and path planning behind a simple yet intuitive UI that anyone can use. So under the hood, the core innovation of our software was the motion planner. It uses AI to generate optimal robot motion. It can guarantee that the trajectories will be collision-free and singularity-free. And of course, it is robot agnostic, allowing us to work with any robot. We couldn't rely on standard drivers. We wrote our custom drivers for each robot brand to ensure precise trajectory tracking. By using low-level interfaces, we bypassed the typical controller lag, enabling real-time trajectory streaming. All of this taught us valuable lessons and helped bring us to where we are today. So we started small, but our vision was big. Today, this is where we stand. We've grown from a small lab team into a company with a culture of engineering excellence. We aim to build the future of robotic handling. Our mission is simple but ambitious, is to deliver versatile robotic automation that is truly easy to use. And we know how to achieve this because we have deep expertise in robotics, AI, and logistics operations. As you can see, our team has expanded to support this mission and drive innovation forward. But we always knew that single case palletizing was just a warm-up. So the real challenge, which is called from many the holy grail of warehouse automation, is on-the-fly mixed case palletizing. And why is so hard? Because it's like playing real-time 3D Tetris. So where boxes arrive in random order with no presorting, they vary in weights, dimensions, fragility, and the system, either a human or a robotic system that does the palletizing, should decide instantly in order to ensure stability and density. So to solve this, you need a system that stacks random boxes stably, supports multi-pick operations to maximize throughput, and of course can build stable pallets that can be transported. And the most important part is to do it without requiring sequencing, which means that you can change the order that the boxes come on the conveyor. So that's why we built Anystack, which is an AI-powered solution that handles randomness without sequencing. As you can see in this video, the robot adapts to whatever boxes arrives on the conveyor. So we can say that it sees the chaos and finds order within it. And these are the core module of Nstacks. So the new modules are the box dimensioner and the mixed stacking planner. We utilized and improved the motion planner and the grass planner from single case palletizing. And of course, we reused the robot controller. And it all starts with the eyes of the robots. So we use an industrial RGBD camera mounted above the conveyor. So we don't just take raw information. We capture an image of the box. We do detection, segmentation, outlier filtering in order to get a precise 3D measurement. As you understand, this is a vital operation. If the measurement is not correct, the whole system will fail and probably the pallet will collapse. And this leads us to the brain of our operation, the mixed stacking planner. So the problem statement sounds simple. Stack boxes, okay, but it's not. Mathematically, it is a multi-objective optimization problem. So we are trying to create stable, high-density pallets that maximize the space above, that maximize the empty space. The planner doesn't just look for space. It has to balance between three criteria simultaneously. First, maximize space utilization. We hate shipping air, so do our customers. Second, we have to ensure that we build stable pallets. This is non-negotiable from everyone. So if the pallet collapses during transport, the efficiency gains don't matter. And finally, we have to build tight and structurally sound pallets. And this is where we diverged from traditional coding. Rather than hard coding thousands of stacking rules, which simply wouldn't scale, we turned to reinforcement learning. So we didn't have expert data. That wasn't the problem. Instead, we let the AI agent learn through trial and error exploration, simulating millions of steps to discover optimal pallet layouts. And this is the result. So the result is a robot agnostic planner that evaluates thousands of combinations to find the best placement, maximizing the criteria that I described earlier. So what you are seeing is the decision-making process. The system analyzes the topography of the pallet, simulates thousands of potential combinations in a fraction of a second, filter out unstable placements, discards inefficient ones, and identifies the optimal placement. In essence, it plays out the future of the stack before even the robot moves. But as I mentioned earlier, stability is vital. So we ran physics simulations during evaluation of our model, but we also ran tests on our stacks in the real world, literally pushing them with forklifts to ensure that the AI predicts what AI predicts as stable truly holds up. Once we know where to place the box, we utilize the improved motion planner. So the next step is to get the box there safely. So we improved the motion planner that we developed during single case palletizing. Our path planning is voxel agnostic. So whether it's a straight motion or a complex trajectory around obstacles, the system dynamically generates the optimal path in real time. And one of the most interesting insights from our experiments is the buffer effect. So what is the buffer? The buffer is the number of boxes the robot has available as options. So in our case, is the number of boxes that are on the conveyor. We observed that the pallet fill rate improves as the number of available options increases. So in other words, giving the AI more choices allows it to make smarter placements, boosting the overall efficiency and performance. And here is a video, which is a comparison of how a human performs mixed palletizing versus our system. Of course, the boxes aren't identical, but this will give you a clear idea of the difference. So here, the human search for every possible placement while, sorry, search for every possible placement, while our system dynamically adapts to every incoming box. So in other words, our agent does in milliseconds what would take a person much longer. On slide, to support our global growth, we need the best engineering. So we are hiring. We are looking for people who want to tackle hard problems. Specifically, we're seeking for an ML engineer passionate about reinforcement learning with an expert in CUDA. So if you want to build tech that actually ships to warehouses worldwide, visit our website, progressiverobotics.ai. Thank you very much.